Welcome, everyone. I'm going to start with a land acknowledgement. I want to honor my grandmother and all the grandmothers from the Nisquamish community of the Accompanying Nation. I also want to honor the current and ancestral stewards of the land that I'm speaking to you from, which is the traditional and still occupied territory of the Squamish, Tsleil-Waututh, and Musqueam people. And I'd like to ask you all to take a moment and honor the current and traditional stewards of the land that you're calling in from. So please do that before we get started. I'm feeling a little nervous too. John asked me to do this yesterday, so I've been sort of thinking about what I wanted to say. I'll introduce myself. As I said earlier, my name is Janice Abbott. I have worked in the nonprofit sector for the past 30 years. I've known John for probably 22 or 23 of those years. Really excited when John asked me to step in an interim role with Kelp Island. And I've been trying to think about what it is that excited me about this opportunity. And I think for me, kelp farming holds a promise that's rooted in First Nations wisdom and respect for Mother Earth. It honors our responsibility to care for the land and sea, absorbing carbon and restoring balance. Sorry about that. It's a sacred food source, rich in nourishment and connecting us to our ancestors and the wisdom of our elders. It holds the promise of economic sovereignty, fostering local livelihoods and community resilience, and empowering First Nations communities to reclaim economic independence. Through bioremediation, kelp farming also holds the potential to help heal the wounds inflicted by colonization, revitalizing our waters and ecosystems, and it offers a pathway to decolonization, honoring Indigenous ways of knowing and being in harmony with the natural world. So I think that's why I'm excited about being here and why I accepted this opportunity, and also the opportunity to work with John. So yeah, I appreciate being here, and I'm going to give you a bit of a run of the show. So John is going to speak for about 45 minutes talking about Kelp Island. We'll then have some remarks from Dean Stanky and Margie Rule. We'll do some questions following. I'm going to try and keep track of questions, and when I get to you, if you turned your camera off, I'll ask you to turn your camera on when you ask your questions, just so we can get to know each other a bit better. And I'll pay attention to the questions in the chat. And with that, I'm going to turn it over to John. As I said, John and I have known each other for 20 plus years, originally starting in the sort of social justice movements. And this is still social justice work, just a different kind than the social justice work we did when we met. So John, founder of Kelp Island, over to you.
All right, thank you so much, Janice. And for those that just joined while Janice was speaking, Janice is the incoming CEO of Kelp Island. So thank you very much, Janice, for stepping into that role. I'm also happy to acknowledge Ori Lavalli, who's the CEO of Kelp Island Australia. For those that are just joining, this is actually the kind of the culmination of quite a process. Just one administrative note. I'll ask folks to turn off their mics while we're doing the presentation. And if a question comes to your mind and you don't want to forget it, just type it in the chat. Janice is going to be watching the questions, and we're going to circle back at the end of the presentation and cover a bunch of questions. And I think that's going to be a pretty important part of the day today. I'm also kind of keep on admitting people into the room. There's a lot of people coming. So just look at my notes here. Oh yeah, I was saying, I just want to kind of acknowledge all the folks that have been involved in the development of this strategy. You know, this is kind of the combination of we've had 4 dry run sessions. We've had about 30 to 40 people participating in those, giving feedback, multiple drafts of the strategy, following upon our nomination by Ashoka back in November for the Earthshot Prize. So it's lovely to be nominated. At the time, we indicated that we had some big plans, or that could have plans that could have a major impact. And this is the follow-up presentation. So what's going to happen is we're recording this presentation, and the presentation, together with a technical white paper and some modeling spreadsheets, are going to be forward to the Earthshot Prize Committee, and it's going to be shared with all of you. And we're kind of in an iterative process here. I don't think that we're at the end of the road in terms of the modeling, of the projections, the plans. So I'm really keen to hear all of your feedback as we kind of iterate and continue to refine this. So please regard this as a work in progress. This is a living plan, and hopefully with your input, it's going to get just better and better and better. And I think it's already looking well, pretty inspiring for me anyway. So I'm going to speak. I'm going to do this presentation. It's about a 30 slide deck. And then we're going to invite Dean Stenke and Margie Rule to say a few words. And David Oliver, if he's able to come. He wasn't sure. I didn't put him on the list because he wasn't sure if he'd be able to come. He may join, but he's also one of our experts and a carbon sequestration expert that has been quite involved in all this as well. So with that kind of preface, and Janice, can I ask you to let people in, as I'm still seeing a lot of names coming up, and I'll just focus on the presentation. So here we go. I'm going to share my screen, and then we'll just launch in. Okay, here we go. Thanks, everyone. Kelp Island is our organization. We're actually a two-part organization. We have a non-profit organization as well, our Seabrick Society. The mission of both really is to address climate change through seaweed-based materials design and product innovation. And I'm just going to mute occasional people. I'll ask folks, if you're not muted, just to mute your camera just in case there's background noise or such like. So Kelp Island was established a couple of years ago. We've attracted quite a wonderful group of people, actually. And so I just wanted to acknowledge some of the people that have been involved in our work to date. Some of them are here in this room and have been involved in, helping to design and refine this plant. A lot of engineers, but also carbon experts and entrepreneurs as well. This is definitely kind of the bleeding edge of climate change technology. We've also had, I want to acknowledge, some of our allies and partners. I saw, and I haven't been able to keep track of all of the people coming into the room, but anyone from UBC, I want to acknowledge you, and Construction Foundation, and particularly I want to acknowledge anyone from the Healthsick Nation. I saw some folks from Healthsick Nation signing up. Thank you very much for joining, and I'm not going to go through everyone, but thank you all for being a part of this. So I'm going to just lay a bit of context about the problem and Kelp Island, and then I'm going to go into our Earthshot presentation. So the first bit here is just really kind of saying a bit of context. And the big part of the context is just seaweed is amazing. Brown seaweed in particular. I'm a big fan of brown seaweed, and there's actually 4 different kinds. There's brown, red, and green. And red is kind of the most popular in a way and used for a lot of food, but brown is, I think, where a big opportunity lies. And you might have heard of sargassum, and the photo in the top there is sargassum being cleared from the beaches of the Atlantic. It is actually kind of grown to huge proportions and washing up on beaches and huge source of pollution. And also kelp, my personal favorite. Giant kelp will grow up to 2 feet a day. It's the fastest growing plant on the planet by a very significant margin. 2 feet a day, it's kind of an amazing thing. And what's really also amazing about seaweed is that it sequesters an enormous amount of CO2. It's 40%, I have CO2 there, it's actually 40% carbon by dry weight. And that's almost all atmospheric carbon. It just pulls it from the atmosphere. It's also a very useful product. So it's used in foodstuffs, ice cream, salad dressing, all sorts of food. You'll be surprised how much of your food contains seaweed. It's also used as a fertilizer, a feedstock, bioplastics, cosmetics, pharmaceuticals. It's used just in a very broad, surprisingly broad range of products. Brown macroalgae, and I'm going to be focusing on brown macroalgae. So brown seaweed, like sargassum or kelp, really divides in the processing, divides into 2 pieces. There's the extracts. And the extracts is really where all the economic value is of brown seaweed. And this is where They squeeze the seaweed, they treat it, and they extract this alginate. A lot of it's alginate, but there's other things in there. And this is what kind of goes into the commercial products. The fiber that's left over, they call the residue, is actually pretty much a waste product. It's sometimes used as chicken feed or landfill, but it's where almost all the CO2 that is sequestered in the kelp or seaweed lives, and it's often it doesn't fetch very high prices, so it's almost a waste product. So those of you that know a little bit about our work know that so far we have, in collaboration with the University of British Columbia and the Bioproducts Institute, been able to take that kelp fiber out of brown macroalgae and process it into a strong structural composite. And so we're calling it kelpstone. And some of my engineering students are in the room today, so welcome. It's kind of an amazing product, I think. It's 3 times stronger than standard concrete on a compression test. So the engineer's room, that's about 60 megapascals compression strength, incredibly strong. Because it's made primarily of the fiber in the kelp, it's about 50 to 60% carbon by weight, so half of it's carbon. Very easy to manufacture, doesn't require any kind of advanced technology, and it's low cost. In large production, it'll cost about the same as concrete, which is kind of shocking to think about. And it's going to be able to replace concrete and plastic and fiberboard and wood in many kind of applications, provided that we can get the kelp fiber in the volume that we need. We have kind of taken it a step far. We have a kind of a longer plan that I'm going to be laying out. We've got this kelpstone. Our plan is to fasten the kelpstone into sea brick, and we've been modeling the form of the sea brick. I think some of the people that have been working on the sea brick component of the project are in the room as well. Welcome. So the plan is to take this kelpstone, compress it into hollow modular floating bricks. So they connect together. This is not the final design, but it's kind of a good prototype of it. They are coated with a polymer shell. It's a biosafe shell. There's a number of different approaches, but not harmful to the environment. They'll give the floating bricks about a 75-year life in an ocean environment. So that is kind of our next step in our kind of technology progression. But we have the core components, and we just have to put them together right now. And we're taking aim at, I would say, construction, and in particular floating construction, because those of you who don't know, floating concrete, there's a lot of it produced, is not just concrete. It actually contains a lot of steel as well. 2% of the volume of floating concrete is steel. And actually, the steel in floating concrete is responsible for more emissions than the actual concrete in floating concrete. So it's a pretty high emissions product, but also the only thing that is really available if you want to build seriously on the ocean, unless you just go with straight steel, like a ship or oil rig. But this floating concrete and steel is kind of the main option. Where we go, once we have sea brick, in this modular system, is designed to be able to make different kinds of shapes that are useful for marine infrastructure. It's got a kind of a locking system that won't come apart very easily. There's a lot of kind of design considerations that gone into this, but it comes in triangles and squares. And with triangles and squares, there's lots of toys, kids toys that play with this kind of geometric dynamic. But you can make a very broad variety of shapes if you have triangles and squares. And of particular interest to us, aside from circles, is the ability to make hexagons, dodecagons, which is that 12-sided shape you see there, and really just a very broad variety of shapes, trapezoids, rhombuses, etc. So it really, unlike Lego, which is square-based, integrating triangles into the design format opens up a lot of doors of possibilities for architecture. So we can create these modular bricks that fit together in a lot of different ways. And if I just flip back, you see these little holes that appear when you put the bricks together. Those are the positions where tension cables go in. So tension cables are used to squeeze different layers of bricks together. And with that, we're able to create 3D structures, in particular tubes and pipes. And tubes and pipes and cylinders and rods are we're going to come back again and again to these, because it's one of the fundamental pieces needed for marine infrastructure, particularly for the kind of seaweed farms that we're going to be talking about. So we can start to make these very large, somewhat intricate objects using these brick systems. And I'm not claiming that we're at the end of the road for the brick design. There's going to be ongoing improvements, and a couple of conversations in the room are about, you know, the actually having a contest to further improve the design, but this design is possible. So if we look at the math of, you know, kelp stone and sea brick compared to floating concrete and floating steel, it's competitive. And I think this is where some of the opportunity starts to be realized. If we look at these materials as being based on their value, how much weight can they support? How much money does it cost to support 1 ton of weight? Sea brick and kelp stone are quite competitive, and particularly if we use the sea brick to create floats. And floats are basically hollow cavities. So if I go back a slide here, we can seal the gaps in between bricks with sealant, so that a wall of these bricks becomes an airtight or a watertight chamber. So we can use these bricks, just like floating concrete has a hollow interior and floating steel has a hollow interior. We can use the bricks to create hollow boxes or floats that will float. So when we use them to create a float, it's a very mass efficient way of creating a floating structure. Cost about $400 per ton to float a ton. So that's a bit of the economic background of you know, floating infrastructure. It's a large market. There's about $91 billion spent every year building docks and offshore platforms for marine infrastructure. The general market for sustainable construction is about $350 billion. So these are alternatives to concrete, hempcrete, bamboo, and all these other things that are making such inroads. And then the overall market for construction materials, vast. Yes, $1.3 trillion, and that includes a $600 billion market. So there's a lot of money, a lot of investments going into materials to build infrastructure. And so if kelp can be scaled, there's a big opportunity for kelp here. There's also a big opportunity just in the idea of carbon sequestration itself. I mentioned earlier that this kelp stone is about 50 to 60% carbon by weight. This whole carbon market, carbon credits are growing very rapidly and well. There's going to be about $200 billion market over the next 10 years. And by embedding the carbon in a brick, which becomes infrastructure, which can be sunk or repurposed at the end of its life, is effectively a semi-permanent form of sequestration. So a little bit more of the background of kind of what is possible. We're early days, and I'm not going to be spending a lot of time on kind of what we're doing aside from the Earthshot pitch, but I just want to let you know we have partners already that are, you know, planning on using this kelp stone for products such as Total Totem in California. It's going to be making wall tiles using the kelp stone, and we have an agreement with an artist in Bella Bella, and we're going to be making coffee coasters using some of her art. This is just a shout out to Blake Carpenter if she's in the room. We're all kind of thrilled about, you know, the art that she's produced. So I saw Bo Reed join a few minutes ago, so I just want to say hello to Bo and anyone else from Bella Bella. We're very proud to be partners with the Healthsick and have been for more than a year now, thinking about how can some of the opportunities around seaweed be manifest for the Healthsick and other First Nations along the coast. The Healthsick in particular, I think, are facing a wonderful opportunity. They have about 1.5 million kilograms of kelp in their surrounding waters that they can sustainably harvest each year. And this is without any farming whatsoever, just these vast kelp forests. And I think kelp farming is an opportunity that many Indigenous coastal communities are looking very hard at now, as the fishing industry is tailing off and forestry is also tailing off. Many of these communities are looking for new opportunities, and kelp is coming up more and more. And luckily, for many of these coastal communities, they have an ideal habitat for kelp. And and is enormous potential. So that is the background. And I tried to keep it brief just to give you a bit of a sense of the company and the organization and what we've done so far. So what I'm going to do now is I'm going to speak about how we can take what we've got in this plan and use it to hit some of the Earthshot Prize objectives. And Earthshot, for those that haven't looked it up, is a $1 million prize. It's awarded by a bit of a who's who, and it's really for initiatives that will move the dial on climate, like seriously move the dial. And unfortunately, and this has been remarked upon by many, there are not a lot of carbon sequestration initiatives that will scale to meet the level of emissions that humankind is putting out into the world. You know, we are just putting out a vast amount of GHGs, and it would take a vast amount of sequestration to even match it, and we're nowhere near matching it. And there aren't really any options on the table for actually scaling our sequestration. So that's the nature of our pitch. We are putting out that we could reach global net zero. Let me just give a bit more of the background. Yeah, I'm going to talk about this. Okay, so before I get to the good side, this is where we are right now. And you may have read the news a couple of weeks ago. We actually hit 1.5 degrees warming last year. And so, you know, people have been talking about this being some point in the future, but we hit it last year. And so we're far ahead of, you know, climate predictions, and not a good way. And if things keep on track, we're going to have more than a couple 100 million climate refugees. We're going to have 250,000 people whose homes will actually be underwater in the next 50 to 60 years. Most of humanity lives close to the coast. And that also includes about 12 million kilometers of lost farmland. And this is going to create a lot of human conflict and ecological harm. We can just see it coming down the road, all the disasters that are going to follow. And, you know, many of the conflicts of human history, if you look back, have been driven by environmental pressures. And so I don't think our coming 50 to 60 years is going to be spared. So it's really kind of a desperate problem. The hope and the opportunity that we're, you know, dedicated to advancing is this idea that in 50 years, seaweed farming could enable us to achieve a global net zero. So by global net zero, we mean our level of emissions is met by our level of sequestration. We are no longer emitting an excess of GHGs into the atmosphere. So the warming will stop. We could also create a lot of housing using the construction products that seaweed could create, and an enormous amount of food. You know, one of the big products of seaweed is food and foodstuffs and fertilizers and all that. We're going to be able to generate an enormous amount of volume. It would take 1 million kilometers of 1 million square kilometers of seaweed farms. That is, you know, a pretty big number. And I just want to contextualize that a little bit. But our position is that it is possible, and quite possible. Before I go on here, I just want to talk for a moment on this 1 million kilometers squared. We have been working on projections and modeling of the impacts here, and we're getting a range of numbers, you know, based on different assumptions, as you might imagine. On the low side, and I'll say this 1 million kilometers squared is on the high side. On the low side, it could be as little as 100,000 square kilometers. So it's somewhere in that gap between 100,000 and 1 million. And at the end of this presentation, I'm going to share my sheets, and I can invite your feedback, because we obviously want to get a little bit more precise. Is it 100,000? Is it 1 million? It's somewhere in there. I think it's actually going to be closer to 100,000. But this is where I'm really going to invite all of you to take your boots to the numbers, really look at them, and see if, you know, we're making mistakes, or if we can get more precise in some of this. But anyway, even if it's just 100,000 square kilometers, it's a lot. So how can we do this? We certainly can't do it with our existing technology. But my proposition that I'm going to be advancing is that it is possible with the infrastructure. And infrastructure is not something that people really think of when they think of seaweed farms. They think infrastructure for seaweed farm. What is infrastructure for seaweed farm? Well, it's floats, it's ropes, it's maybe some weights or anchors, but that's not what we're talking about at all, actually. So I'm going to be putting forward to you a kind of a new way of thinking about seaweed farming that is very infrastructure oriented. And it really goes to the heart of kind of the opportunity that seaweed presents. And there's been a lot of promise. Seaweed has had a lot of promise. A lot of prizes have been awarded for innovations around seaweed. Brian in the room here is a winner, and there are other organizations. It is an amazing material, but it's proving very difficult to scale. And this is because production cost is high, volume is low. We have not arrived at the part of having industrial level agriculture like we have with wheat farms or on the prairies, where you can just have the giant combine harvesters going across. We don't have that. We have systems based on ropes for the most part. And here's a harvester you can see there. They're pulling up ropes and taking the seaweed off the ropes. And before I kind of go more into infrastructure and what a possible design of seaweed farms could look like, I just want to talk a little bit about seaweed itself and make some distinctions. So red seaweed, as I mentioned before, is the most popular seaweed. It's used a lot in food. I did a little bit of a graphic here so you can see a bit of a comparison. And in many ways, they're similar, but in many ways they're quite different. And especially red seaweed is quite short. Generally it's usually small. It doesn't really get taller than a few meters, like a bush. Brown seaweed can be floating mats like sargassum, it just drifts along the surface. But the one that is most interesting to us is kelp, and giant kelp or bull kelp. Giant kelp in particular, this is the one that will grow 2 feet a day, and it grows tall. It can grow up to 65 meters tall. It's incredibly tall. 20 to 30 is not uncommon at all. So it's more like a tree compared to a bush. And it has a trunk, it has a root system. Unlike a tree, the roots don't suck nutrients, but they hold on to things. It's called a hold fast. So this is kind of the nature of a kelp or giant kelp. Quite morphologically different, actually, from red seaweed. And that's important context because it really goes to, well, how do we farm efficiently? And current models of farming rely upon ropes. So the ropes provide both the infrastructure and the substrate for the kelp or for the seaweed. So, and kelp too. So the ropes are usually seeded in a nursery, and then the ropes are used strung in rows like this. There's a number of different designs, but it's rope based. And unfortunately, this is not ideal for big kelp plants. Firstly, because usually these farms are located just a few meters below the surface, so the kelp doesn't really get a chance to grow to its full height. And also, rope is not an ideal substrate for the hold fasts of kelp. They're not evolved to grow on ropes. They're evolved to grow on rocks. And so it's a bit of a square peg in a round hole when it comes to farming giant kelp. Ropes are not quite ideal. And the problem with ropes is kind of arises on a few occasions. Even the biggest farms in the world, and I show a picture there on the left of a South Korean farm, absolutely a massive farm, but still rope based. So they're going along, pulling rope into the boat. That is a shallow water farm there. Deep water farm would be, here's a picture of a deep water farm in the middle there. This is from Climate Foundation. Again, you see the ropes and the floats, and there are some limitations in the design. It's hard to think about how we could harvest seaweed growing on a farm like that at the same kind of scale as we might with industrial combine harvester on land. And these ropes, everything revolves around the ropes. So this limitation. What we need really to get to where kelp could really move the dial on climate is we need to be able to harvest kelp, like I say, like a wheat combine harvester harvests wheat. We need to have farms of kelp that stretch to the horizon, just solid, and we need seaweed harvesters that can compete. And I've got a little picture of something that kind of goes along that length in the lower left. but that's a seaweed harvester, but it's actually not for farmed seaweed. That's for naturally growing seaweed. It kind of goes along and scoops it up. Um, and, and we need to be able to deploy that kind of technology at a larger scale for farmed kelp. So I'm going to take you through now kind of vision of how, starting with kelpstone and then sea brick and then structures, we can get to an infrastructure that can support large operations of growing kelp. Here on this screen, we see some examples of existing technologies. On the left, you see kind of a rope-based ropes in rows. In the right, you see kind of the circles that are being pioneered by Climate Foundation. Challenges, it doesn't cover a lot of space, and also dependent upon these ropes and floats. They're kind of, they get in the way. Right? So now I'm going to walk you through what basically our proposal is. So step one, we lay beams in a horizontal or in a hexagonal grid. So they're laid horizontally, and the top image here shows a top-down view, and the lower image shows a side view. So these beams would be maybe 15 to 20 meters long, like a telephone pole, hovering 10 to 30 meters below the surface. And with this approach, it's kind of the mathematically most efficient way of covering space. I have a background in mathematics, so I love hexagons and their efficiency. So this is kind of the first foundation layer of this farm, these beams that are laid on a grid. Secondly, over top of these beams, we lay a mesh of hexagonal webbing made of cable. And each segment of the cable may be 1 meter long. Where we differ from traditional ways of farming seaweed is here, the cables or the ropes are not used to seed the seaweed. They're just structural, and they could even be made of stainless steel. Well, we do want to stay away from stainless steel, but we're not preoccupied with trying to make kelp grow on them. And we don't have to cover the whole space with this mesh. We can cover some of the hexagons with the mesh, and others leave it open for light to penetrate through to the lower levels or for sea creatures to get through. Over top of the mesh, we place what we're calling grips. So these are basically fake rocks that are clipped onto the intersection of the cables of the struts. These grips could be seeded in a nursery or in shallow water and then moved and placed onto the mesh when they're ready. And it wouldn't be very big, 20 centimeters, 30 centimeters. They could be reinforced inside, but they're going to live on the mesh, on the beams, about 10 to 30 meters below the surface. So significantly deeper than traditional rope-based farming. And so here's a bit of a diagram of what it could look like. This is a basic grip. Here's a 3-part grip here. It clips basically over the intersections of these struts. The holdfasts will grip onto these fake rocks. It's really what they're evolved to do. And the holdfasts are actually, a great form of habitat themselves. Things will find themselves living in those holdfasts. So where does this get us? It starts to get us into scalable kelp coverage of the water. We can, lay the mesh over selected hexagons. And because there are no ropes or floats that are penetrating to the surface, we can now deploy industrial harvesters that will take the top 1 or 2 meters, like a haircut, basically, or a lawnmower going across grass, and leaving 80 to 90% of the kelp plant intact to grow back. And actually, that last 2 meters of growth is really where kelp always does its spurt. So kelp will grow back very quickly to fill that. In fact, kelp is used to losing up to 50% of its mass per year just due to breakage. It's evolved to lose mass. And so this approach allows us to kind of scoop off that top 1 or 2 layers without getting tangled up in the ropes. Now, there are some engineering questions that arise here. Well, how do you keep these things how to keep these beams horizontal, not sinking or crumpling or floating away. And when you're in coastal areas, you could use traditional methods, like you have anchors and ropes. You can have floats. And so on the left-hand side of the lower diagram, you can see I've got some floats and ropes just holding it in place. It's important to know that kelp is very buoyant. A 20-meter tall kelp plant will exert an upward force of about 50 kilograms, which means that if it's gripping onto a rock that weighs 40 kilograms, it will lift it up and pull it away, just from the buoyancy of the kelp. So there's usually a strong upward force that a grown kelp plant will exercise. So we have to think about both the sinking down and the rising up. So here, as we get into deeper water, we can abandon the need for anchors and go with what we're calling baskets, which are basically scaffolds that have a float on top that hold the base at a fixed position below the water. Maybe it's 10 meters, maybe it's 20 meters. It doesn't require an anchor to be fixed at the bottom. And the advantage of using a scissor scaffold, like is portrayed here, is we can actually raise and lower it. These scissor scaffolds, it's pretty standard technology, but deployed here, it will allow us to raise and lower the bed of the kelp, which has a lot of value because, when the kelp are young, we might want to have it at a higher depth. As they grow, we lower it. Maybe for harvest time, we raise it again. There's a lot of value in being able to raise and lower it reliably. And note here that it also makes us independent of anchors. And that's very important. And being independent of anchors and ropes is actually very critical because these are often in intertidal zones. Water coming in, water coming out, currents. Trying to maintain a fixed position in the face of some of these marine forces is very challenging. But if we can let go of anchors and ropes, then at some point we can move into floating farms. And I'll talk a little about that too. Along with baskets, we can also have what we're calling just spars. And a spar is essentially a big hollow cylinder that might be capped at the top that has a tube going down into the water below it. And it might, I got a little red square there showing it. It can be powered by wave action. Water comes in to the spar and goes up and down with the wave action. So when you have that kind of dynamic, you can deploy a broad range of different power converters. They're called point energy converters. And they just go up and down and they generate power. And they can also act as a pump. So by using infrastructure, we can create these larger enclosures that can protect an energy harvester and allow it to become a pump pulling water up from the deep. And why is that important? And I see on the lower right, you see there's a kind of a darker blue water. Well, this darker blue water is actually the key to rapid growth of kelp because it's very rich in nutrients, and getting that water to the surface so that it can feed kelp with the nutrients, with other stuff that is in there, accelerates kelp growth. So a lot of the permaculture initiative that Climate Foundation has been leading is exploring different ways of exposing kelp and seaweed to this richer deep water, either by bringing it up or by bringing the kelp down. In this model, we're proposing that we bring it up and we use the wave-powered pumps inside spars to do that. And these can be part and parcel of the overall structure of the kelp farm. A wave break in this context is not maybe what you think of in a normal wave break. We're not trying to stop the waves here, actually. It would be kind of more like a shallow pontoon, maybe 10 meters wide, maybe 1 meter deep and long. And it really just kind of smooths the surface chop. This makes the waves a little bit smoother. The waves still go up and down. By removing the surface chop, you reduce the amount of breakage of the kelp. And also you can create an enclosure space where when kelp does break, you can capture the floating kelp before it drifts out to the ocean. So it kind of contains it. And you can also create habitats on these breaks, and you can use them as points for energy collection. But I suspect that some kind of break, wave break, if only to smooth the water somewhat, is going to be a valuable component here. And sorry, yeah, there's always one mistake. I missed this one here, but please ignore the box on the left and just focus on the picture here. This is a picture of a floating farm. So here we've left behind the anchors and the mooring, and now we have a floating structure. It's got the beams 10 to 30 meters below the surface at which the kelp is growing out. Those beams are held in place by the spars and the baskets, and it's surrounded by a wave break that can actually grow as the farm grows. And so this would be a version of a floating farm, and it would be highly productive. So we can move away from having moored farms in coastal areas to having open ocean farms in deep areas and having open ocean farms that are large. So this kind of design of an open ocean farm can keep on growing and getting bigger and bigger and bigger. You know, it just keeps, you can keep on adding more and more to it. And you know, it does raise issues like, well, how do you steer the thing and where's it going to go? And these currents, where do they take us? Well, there's actually a lot of opportunities to deploy locomotion systems, not like a boat where you can get A to B in, you know, a bunch of days, but no, something that can get you moving a few kilometers a day. And when you can do that, you can ride currents. And there's a lot of current gyres that will take a floating farm or a floating mat in circles, and a lot of places in the ocean that are good positions for this. And I'll talk a little bit about that. So this is where we get to with the floating farm design. Another point, and it's kind of, this is not my idea at all. This has been well established by farmers such as Greenwave and others, that you can co-locate other food products with kelp farms. So they're great habitat for fish. Studies have shown that the bycatch of fish around a seaweed farm will go up to by as much as 2 times, increase by as much as 200%. And those are just for small seaweed farms. We can integrate baskets and trays into this farm design to cultivate shellfish. And the picture on the top right shows you some of the designs that Greenwave has been putting forward. It turns out that shellfish and seaweed love living together. You know, they kind of consume each other's waste products. The shellfish filter the water, the kelp remove CO2 from the water. They all do better by it. And also, if we deploy these spars to bring upwelling from deep water, we will also be feeding not only the kelp, but we'll also be feeding the phytoplankton and the zooplankton that feed on the phytoplankton and the whole food pyramid that will get us to the fish and the shellfish too. So there's a lot of opportunity here to create a very ecologically rich resource. And if we deploy them in deeper water farms in an area that is not particularly biodiverse. Deep ocean actually has less biodiversity than the harshest desert on the planet. And so I shouldn't say biodiversity, less biomass than the harshest desert on the planet. So deep ocean really is the place where we can do the least harm if we're going to be deploying regenerative carbon sequestration technologies. In fact, we may be able to do significant good. So there's different approaches. This design, we're not saying this is going to be the end all and be all. What we're trying to do here is show it is possible, actually, by using infrastructure to get to large scale seaweed farms. And well, the question boils down to, well, how much mass are we talking about? How much infrastructure would we need? And here's where it gets into, a lot. So to do 1 million square kilometers would require well, if we did it with floating concrete, it would it would be about half of the world's total CO2 budget last year. So 15 gigatons of CO2. It would take us that much to build a concrete to do such a farm. It would take all the world's output for almost 40 years to make the wood to build the infrastructure. So they're both really out of the question. But seaweed can provide this infrastructure, and it's because the seaweed is being grown by the farms as they grow. And so the two can go in lockstep. In fact, we can have kind of an exponential feedback scenario. And I got a couple of little analogies here of how much is 1 million kilometers squared. In some ways of looking at it's a lot, but comparatively, it's about 2% of our current agricultural land. It's less than 0.5% of the ocean. And it's much less than how much farmland we're going to lose in the next 50 years because of climate change. So you could almost view it as a catch-up or a replacement. If it turns out that we only need 100,000 square kilometers, then we're looking at just the farmland of Iowa. Can we build kelp farms to cover the farmland of Iowa in 50 years using a design like this? Well, I think it's certainly within reach. And if we could, the win is huge. So how could we do that? This is where I think I'm going to take a moment here just to dwell on this page here. We're all, having gone through COVID, aware of, or maybe many of us are aware of R. This is kind of the reproduction rate of a virus. And, some viruses are more catchy than others. They have a higher R and they spread more quickly. We can look at a seaweed farm as kind of growing like that, because as a seaweed farm grows, it's seaweed. That seaweed can be turned into bricks that are used to grow more seaweed. So we get into a feedback loop where the product becomes the infrastructure, becomes the product, becomes the infrastructure. And that allows us to get into kind of what's called an exponential feedback loop. And this is where we can start to achieve scale very quickly. We won't run out of infrastructure. We will have the infrastructure we need because the seaweed farms themselves will be producing it, and they'll be producing lots of it. And so this graph here just shows how the growth pattern would go. And I think what's interesting about this graph, and it's like, what does this graph even mean? It hasn't got even labels on the graph. What does it mean? Well, the key thing is this graph really corresponds to the amount of CO2 sequestered, the amount of concrete placed, the amount of food produced. It's the same graph for all of them. And it's kind of got an elbow on the right-hand side. It shoots up abruptly. Well, what's interesting about this graph is that if you zoom in to the first 10 years, the graph looks exactly the same. It's zooming up at the last minute at any level of depth. And this because it's the nature of this exponential feedback loop. It's one of the few ways that we can truly scale infrastructure by having this kind of graph. And we're able to do it with using seaweed as infrastructure. And this is based upon two assumptions. One, and I call it the mass efficiency. How much mass does it take to build 1 square kilometer seaweed farm? And then how much mass does that 1 square kilometer seaweed farm produce in 1 year? So it turns out that using this design that I've kind of walked you through, we have a very mass efficient design. And that's very important. It turns out that 1 square kilometer of seaweed farm designed in this way can produce enough mass to replicate itself in 1 year, right? In 1 year, it can reproduce itself. Obviously, we're not going to be able to take everything that a seaweed farm produces and use it to build more seaweed farms. You got to pay for itself. There's operating costs, there's return to investment to investors. But if we took 30% of the mass produced by such a farm and reinvested it in building more seaweed farms, then we have an R rate of 30%. And this will get us this graph. So if these two assumptions can be correct, the mass efficiency being about 1, retained surpluses being about 30%, we will have this kind of exponential feedback loop, and we can hit the targets. What does that get us economically? I think this is always an important question. It's actually also, because it's so mass efficient, it's very cheap to build. It will cost us about $20 per square meter to build this kind of farm. And it would cost about approximately, and this is just spitballing, about $10 a square meter to operate. And that would include the shellfish operations. We would make a profit, or whoever runs these farms, because we're not going to be doing it necessarily, would be making about $20 per square meter per year, provided they use industrial harvesting technologies and, do multi-trophic agriculture in their combined crops. This is 10 times the economic value of organic cropland, which will get you about $2 per square meter per year in terms of net income. So it's because of just the enormous growth rate of the seaweed, but also because the seaweed produces the alginates and these other extracts that are actually very valuable. So it turns out to be very, very valuable cropland. And so this will be one of the drivers, we believe, of the expansion of these kind of farms. So there's a lot of money and wealth to be generated by building these farms and harvesting them. And I think this is kind of one of the points I've been really thinking a lot about. You know, we started this journey thinking about, oh, how can we use kelpstone and seaweed to build these farms? But once we got to the design of the farm, we realized, well, actually, we don't need seaweed at all, at least in the beginning. We could start building this design using salvaged logs. We can use it with concrete. We can use steel or nylon cable. We actually don't need to get fancy with kelpstone or sea brick at the beginning. We will need it in the long term to scale. But in the first few years, we can certainly get a going start just with existing materials. And at the end of this presentation, I'm going to be sharing a technical white paper. And I've gone over, I've shown some nice graphics about a kelp farm, but I'm going to be sharing a technical white paper for anyone that's interested in kelp farming to look through. And we've tried to be as precise as possible about all the components of the design, and we're going to invite all your feedback. So we would start with traditional materials, building these large-scale kelp farms, but after 10 years or so, ideally, we'd be able to shift to kelpstone entirely and away from the coastal areas, you know, which have ecosystems already. You know, it's always going to be a sensitive topic, trying to do massive kelp farms in coastal areas. We want to move into the deep ocean farms as quickly as possible. On this map here, I put dots, all the locations that are good habitat for kelp farms, and actually the size of the dots corresponds to 1 million square kilometers. So if we covered that much space, and it wouldn't necessarily be in 10 dots, it might be in 1,000 dots or 10,000 dots. You know, we may have or 1 million dots of 1 square kilometer farms. But there's lots of locations in the world where these kelp farms could be located, and we have a lot of space to work with. The ocean is a big space. If we can crack the nut of farming in the deep ocean, space will not be a constraint. You know, and that is one of the very few things you can say about any carbon sequestration strategy, is that we're not really facing huge constraints when it comes to space. Sorry, there's a duplicate. So here's another diagram showing this. I love this picture because it's a picture from space of planet Earth, and you can't see any land in it. All you can see is water. And it just illustrates the scale of the ocean that's available. And those 10 green dots you see, each dot is 100,000 square kilometers. So altogether, it's 1 million square kilometers there. If we could do large-scale kelp farming that covers 1 million square kilometers of space, we'd reach global net zero, and we might even do it with less than 1 million. We would house 50 million people with the construction products that we would be able to build with the kelp fiber. We would replace 65 gigatons of concrete. We would produce 60 gigatons of food, and we would generate more than $100 trillion in revenue over the 50 years. It's crazy numbers. And again, I invite your feedback to the sheets and to our calculations, but one way or another, it adds up to very big numbers. And it's due to the scaling factor of this exponential feedback loop. So this, I'm coming to the end of it now. This $1 million prize that Earthshot is offering, here's how we would spend it. You know, we're going to spend, we would spend $250,000 on kelpstone manufacturing plant. We want to partner with allies to deploy kelp farms along this design, this scalable design. We would spend $500,000 on that, with partnerships, hopefully with the health sick and other kelp farmers. And then we would also spend about a quarter of the money on moving the product closer to a floating demonstration project using sea brick itself. And I think that is it. I think I'm pretty much on time. Yeah. So I'm going to share this deck with all of you. There's a link to the technical backgrounder. It's a 20-page document. You're all welcome to peruse it and give your feedback. There's a link to the climate projections. It's a Google Sheet. You won't be able to edit the Google Sheet, but I invite you to make a copy and play with it and share your feedback. And also, there's going to be an invite to our Discord channel. And so we're going to host a conversation about this. And if you have criticisms or find errors or suggest improvements, we're going to invite you to join our Discord channel and share your views. So that is the presentation. So I'm going to kind of wrap it up there. Yep, that's the end of it.
Hi, I'm Marky. I'm a phycologist, or more simply, a seaweed biologist. I finished my PhD in 2012 studying the reproductive ecology and biology of the Australian kelp, Ecklonia radiata, and since then have worked helping set up some of the major seaweed farms in Australia. Most recently, I've been working independently as a consultant to help smaller growers get started and have been advising Kelp Island on their seaweed growing research. Seaweed farming has the potential to provide future food security, climate change mitigation, income for communities, and environmentally sustainable products, all while reducing reliance on valuable land, which will be needed for housing and food supply more urgently in the future. Seaweed grows quickly, although often seasonally, and uses nutrients from the water. They are classified broadly into three groups: the reds, greens, and browns. The reds are very diverse and have a wide range of uses, but are generally smaller in size and have complex life cycles. The greens are popular as fresh foods, things like sea grapes and sea lettuce, and the browns include the larger, faster-growing species like kelps and sargassum. Seaweed has been grown for centuries in Asia, largely using subsistence techniques, which involves villagers in small boats collecting small fragments and tying them onto ropes and string. Kelp is largely grown in Asia as food, like seaweed salad and kombu. This process is a little more industrial, with tiny spores seeded onto ropes and nets. This has also always been traditionally a very hands-on approach. There is also restrictions with rope farming, largely with the effective designs of farms, and growers are always looking for innovative approaches to maximise output per hectare and effort. By using horizontal two-dimensional surfaces covering the entirety of a hectare, Kelp Island will better replicate natural growing populations and potentially produce more seaweed per hectare. It is also not known how seaweed growth rates differ when plants are grown on artificial substrates like ropes compared to natural reefs. Kelp Island are proposing the use of natural stones in their structures, closely replicating natural conditions and most likely to achieve natural growth rates. I have personally worked on farms cultivating macrocystis, and with this species being so tall, it naturally wants to grow upwards. However, it will slow its growth once it reaches the surface and runs out of space. So farmers either have to grow it down deep, where light levels are low, but has space to grow it, or near the surface where conditions are best, but once it reaches the surface quickly, it will stop growing or show reduced growth. Having the potential to raise and lower their structures means that Kelp Island can tailor their array for optimal farming in different locations. Also, because macrocystis forms floats, I've seen it wrap around ropes and tangle into giant spaghetti nests. Growing macrocystis on flat surfaces, where depth can be adjusted, will reduce this from occurring. Kelp Island's innovative design tackles some of the major challenges in seaweed farming, and I'm very excited to see how their novel design will improve commercial farming in Australia and around the world. Thank you.
John, that was awesome. We have a couple of questions in the chat, and then I'll just ask them in order. So the first one is from Roger, and maybe just in an effort to meet each other, Roger, you wouldn't mind asking your question. It's about the impact on animals living within the seaweed forest, and it was in part answered by Brian, but perhaps there's a longer answer.
Is Roger still here?
Oh, sorry, are you asking me to repeat the question?
Yeah.
Well, it's just that very often this particular kind of kelp farming I've not come across before, but I've heard about dredging kelp and dredging seaweed, and when it's all pulled out to the ocean, then animals and fish and insects and all sorts of things come with it and die. And I'm wondering what processes you can suggest to mitigate that.
So Roger, you when in existing processes that it causes the death of creatures, you were saying?
Yes, but if the seaweed is hauled out of the sea, anything that's living in it must come with it.
Right. So there would be some creatures living in the upper canopy of the seaweed that would probably get caught by the harvesters. Unlike, I think, many seaweed harvesting, we're not taking the whole plant. So if it's a 20-meter tall plant, this proposed approach would just take the top 1 or 2 meters of that. And the bulk of the forest will be left. And I see Brian has got a hand. He's probably got a better answer than me. So please, Brian.
Yeah, my pleasure. Thank you, John. There are a number of examples of kelp harvesters that actually have shakers that actually shake the animals off while it's coming in. And keep in mind, John's proposing to take the top meter of a 10 or 20 meter tall kelp forest. So you've got another 19 meters of kelp forest in which the animals can use for their habitat. So partial harvest is a key aspect of this, and the fact that at no time are you taking the entire forest, but actually, this amortizes the seeding over perhaps 6 or 7 years. I believe giant kelp has a ideal lifetime of 6 to 7 years. So you seed once, and you harvest quarterly, at least 3/4 of the year, and that provides a partial harvest. You take the top meter, and the other 10 to 20 meters is available for habitat for those creatures. Thanks.
Okay, thank you.
So we have a couple of questions posed by Ali Byrne. Ali, are you still here?
Yeah, I'm still here. Hi, I'm Ali, and I'm with my colleague Logan. We're kelp researchers at North Island College in Campbell River, BC. Thank you for the presentation, John. That was really fascinating. We had some questions regarding the submerged hexagonal farm and the mesh on it. We've run into issues with biofouling on mesh and ropes. Wondering how you would address biofouling.
Yeah, and Brian, I'm gonna invite your feedback on this because I know you have a lot of experience with volunteers, etc. There will be biofouling. I not having deployed one of these, I can't speculate on the extent of it. The key part that we're interested in is the grip itself, that the kelp be given kind of a head start on getting embedded in the habitat before it's put to ocean. I wouldn't be surprised if over time some of these grips will need to be replaced. They might get other creatures, other volunteers, and part of the design process is creating grips that can clip onto the mesh that can be removed and replaced, at the end of life as necessary. Brian, did you have any other remarks on that?
Yes, I'll just comment that one person's biofouling might be another person's habitat or food or something else, or at least creatures. The principles of permaculture are very much multi-trophic and multi-specific. So when you have multiple species, it actually works better. We found some volunteer green seaweeds are complementing our red seaweeds depicted behind me here quite nicely, even to the point where the green seaweeds, we're seeing better growth of the reds along with the greens. And part of that is the fish that like to hang out actually prefer eating the green seaweed, and we're harvesting the red seaweed. So there's some interesting nonlinear benefits that accrue from actually having multiple species available. It's a challenge in a permaculture to design several species and several harvests that actually work well together, but you end up having much more robustness of an ecosystem when that does occur. And I would offer that you check out our article, which was just published this month on marine permaculture in One Earth Journal, that covers some aspects of this, where we're aiming for multiple trophic levels and multiple species and a sustainable harvest of the sea forest, if you will. So I'll drop that link to our One Earth Journal article on marine permaculture with Dave Holmgren, who is one of the fathers of permaculture. Really honored to be doing this article with him.
Thank you. That'd be great.
Can I ask the other question?
Yeah, we were also wondering about what kelp species you were considering for the submerged farm and the sort of partial harvest methods.
Yeah, mostly we're thinking about giant kelp. It could work for bull kelp, clonia. There's a number of different, but really the tall, fast-growing species that would span a distance of 10 or 20 or 30 meters without really even blinking. So it's really, and so on that regard, it's a bit more constrained than a traditional seaweed farm design. A lot of red seaweeds or green seaweeds are going to want to be much closer to the surface, right? This is really aiming at biomass production, right? And alginate is a valuable, side benefit of that, but we're trying to get seaweed that can grow very quickly and generate a large amount of biomass and sequester a large amount of carbon. And for that, giant kelp is the winner.
Yeah, I think if you're targeting giant kelp, that works. But we work a lot with bull kelp, and we were just kind of thinking like that top meter harvest, you're really having to then filter out where you're cutting, because if you're cutting, that bulb off, you're not getting any continuous growth after that, and you're aiming to cut a meter down. So that's kind of interesting. The other thing that we kind of were wondering about is if you are nutrient limited in your open ocean farming for those kelp farms. Yeah.
The nutrients are going to be a huge part of this, and that is really a big motivator behind the SPAR. And so I'm not sure if you caught the mention of the SPAR. It's echoing other initiatives like Brian has been working on, of pulling the nutrient-rich deep water into the surface layer where it can be accessed by the kelp. And so trying to basically expose the kelp into the same upwelling phenomena that you might have in a coastal area, but doing it artificially, powered by wave pumps. And Brian, by the way, I haven't properly introduced Brian, so I'm just going to introduce Brian. Brian is the founder of the Climate Foundation in Australia and has been a leading voice on permaculture and open ocean farm design, winner of, I think, the X Prize a couple of years ago for your work. So, very honored to have Brian in the room. Brian.
Thank you, John. It's really great to be here. And great question about Neurocystis. Now, actually, bull kelp is different in Australia than off the West Coast. In the West Coast, we're talking about Neurocystis, assuming that you may be there. Neurocystis is an annual species. Turns out there's a fair amount of cost associated with seeding, and harvesting is more manageable. So there are some benefits to choosing a perennial like Macrocystis over Neurocystis, simply because you can potentially amortize that seeding cost over 3 to 7 years. And by the way, I might add to the little grid seeding points that you had there, John, and that is, it's pretty standard these days to seed long lines around 80 meters long in an aquarium. And then even if you had your structure that wasn't made out of ropes, you could wind this long line around your ropes, and then the entire arm of your hexagon is seeding material as opposed to just the vertices. Maybe there's an automated way of doing that. I think that those 80-meter seeding lines are pretty darn scalable in the sense that they're doing that in fairly large quantities. So there may be some interesting innovations there on the seeding approach, but ideally you're only doing that every 3 to 7 years instead of every year. So that's one of the benefits of choosing a perennial.
And I will stand to be corrected by the kelp experts, because I'm certainly no kelp expert. But from what I understand, and just from conversations with Margie, if you have a large enough grip, you can have more than one kelp fast holding onto that grip, and they can be in alternating years. So they may not all be of the same age. So you may actually have a grip that is continuously productive, even as individual kelp plants on the grip die of old age, and they're just replaced by other ones. So it could be, the proof is in the pudding, but this is how it works in the wild.
It turns out the research down at the University of Tasmania that we've helped to sponsor has resulted in some interesting nonlinear benefits. First of all, juvenile kelps tend to do better when you have 10 or more square meters of kelp forest environment around them. There is a lot of self-shading and mutual shading so that those juveniles will stay pretty short until one of the big kelp trees disappears, and then they'll quickly fill the canopy. So there's some interesting things going on there. But the typical spacing is one or a few kelp trees per square meter. And so a density of 1 per square meter is not too far off in terms of having a holdfast, and multiple stipes can come out of a single holdfast for Macrocystis at least.
Over to you, Janice. Sorry.
Yeah, all good. Ali, you got all your questions in, I think?
Yeah, thank you very much.
Awesome. I'm not sure if it's a question or a comment from Sean, if Sean's still here, about jumpstarting the project growth potential.
Yeah, but I think this was before I think I realized that we were specifically talking about growing the giant kelp. I was just yeah, I'm an Alaskan seaweed farmer in eastern Prince William Sound on the unceded traditional territories of the Eyak people, and I also serve the region as mariculture liaison, and I you know, a lot of these existing farms here, none of them have any processing capacity. They've proven that they can grow seaweed, but they don't really know what to do with it. And so seeing a product like the kelp stone and the kelp brick is really innovative. It's really exciting and captivating. And I don't know if there's potential for other species to be, you know, utilized for building materials such as a kelp stone. But yeah, if there's other macroalgae species that would be susceptible to that, I think there'd be a lot of potential for other farmers in other regions of the globe to participate and help scale this model.
Yeah, awesome. So it's a great comment, Sean. So the chemistry that we have, the chemistry pathway that we've developed with the University of British Columbia and Bioproducts Institute is, I can say that it works for brown macroalgae. So this is the alginate-based chemistry. I can't make any claims necessarily to red or green. They have you know, different chemistries. I also pretty aware of the fundamental dilemma that you raised about, you know, they have all this seaweed, they don't know what to do with it, or how do they deal with it, you know? So we're working with the Construction Foundation on a modular kelp processing facility that fits in a shipping container. One is a drying facility, and the other is a basic processing facility that can be is kind of designed for remote communities as kind of a pre-processing before it gets sent to somewhere else for more advanced processing. Something that can just reduce the amount of water is a basic first step, and do a little bit of pre-processing on the site. So I'm happy to follow up on that, because I think that's going to be meeting a need. It came out of our conversation with HealthSIC and just kind of understanding kind of the barriers that they're facing to scaling their kelp production. Lack of basic processing is one of them. So hopefully the solution that we come up with is something that's going to be able to be of use to many coastal communities. Brian, go ahead.
Thanks, John. Turns out most macroalgae species are pretty good producers of cellulose and hemicellulose. And a lot of those cell walls, that's what holds the seaweed together effectively. And that ends up being a great tensile as well as compressive element probably in the concrete as a replacement for rebar. So I think that's helpful in terms of the sea brick. I think there's an opportunity to, let's say, optimize the other 40% of the ingredients to optimize properties and ensure enough resilience at sea. And the medium density polyethylene Legos that go together at sea are an example, but having that kind of flexibility is an opportunity there. And there's a trade-off in flexibility and strength and the size of the structure ultimately. So I think those will be interesting trade-offs to try to develop in this industry. I'll also mention, since you were talking about early processing, we are in the process of developing a transportable seaweed biorefinery that can take raw seaweed as an input, produce multiple products, including a dry pulp that would be suitable for the sea brick as an output. And ideally, any location that it can accept a 20-foot shipping container could accept one of our transportable seaweed biorefineries. So this is an ongoing development. We're working to refine it, and my hunch is that most of the 14,000 species of seaweeds should be suitable for sea brick type of development in the future. Thanks, Tom.
So we have a final question, I think, from Michael Williamson about the economic model.
Thanks very much. I don't know whether I'm honored or what to be the final person here. I'm a CEO and co-founder of Cascadia Seaweed. We've been growing seaweed, cultivating it for 5 years. North America's largest ocean cultivator. We've done macro, saccharina, neogarum, alaria, and a few others. My question is all about the economic model, because we have looked at it from every single angle that a small company can. There's a couple of assumptions in your model that I would not challenge in this form, because I'm sure you have answers to, but some of the calculations are of interest to me. But it's always comes down to the economic model. We've managed to lower our cost of goods of produced seaweed from $16 a kilogram down to about $1 a kilogram. We've got processing sorted. We've looked at the market. In our case, it's biostimulants and sustainable inputs to regenerative agriculture. And still there's a delta between making a profit and losing money, including looking at carbon, by the way. I'm very curious about how the Sea Brick venture, despite the great stuff that it will do for the planet, how it makes money and how it's sustainable. What's the prime driving factor in profitability?
Well, it's going to be so separate and apart from its use in seaweed farms. Is that what you mean?
Well, just the overall business model. I mean, a company is in business to do X to make a profit, and then the rest is usually gravy or bonus. So what's the primary product?
Well, our primary product at this point is kelpstone. So this is taking the fiber, treating it, and making this composite, which is not necessarily going to be deployed in the ocean. You know, we're partnered with Tonal Totem, this company in Oakland. They're going to be making wall tiles
Right.
at the kelpstone, and we have this other partnership doing coasters. But it's generally a potential replacement for a wide range of materials: high density fiberboard, plastic, concrete, even ceramics, or in some cases even metal. So I think that's where the value is going to be in the short term. And the production cost is actually quite low. You know, we can get the production cost of kelpstone close to that of concrete itself. And you know, in many ways, it's a superior product to concrete because it sequesters carbon. You can't pour it like concrete. It's a molded product, so you have to decide your form factor before. But I would say it's more on the line of a high density fiberboard, you know, in terms of where it's going to fit in the marketplace, but one that is non-toxic, that is sourced from seaweed and sequesters, you know, kind of this regenerative carbon. So that is the kelpstone business model. And you know, you can do these range of products. And then there's the Sea Brick business model, which is a subcategory of products that kelpstone can be deployed in. And we're, you know, focusing on Sea Brick because it gets us to the scalable production of seaweed itself, which, you know, is the challenge for everyone that's working in seaweed in this room. We know that scaling the production of seaweed is key. And if we can make this conversion from seaweed to infrastructure, and infrastructure to farming, and farming to more seaweed, then we can hope, you know, the theory is break the loop. And if we can make seaweed farms at the price point that I'm suggesting, $20 a square meter, and then we can have a profitable operation, because growing at that scale with kind of harvesting efficiencies that this would permit would bring the cost of production down significantly.
Okay, thank you.
We got a couple more minutes. Janice, were there any more questions?
Possibly a comment from Colton, if you.
Oh yeah, Colton.
Oh yeah, I was just on talking about how sea brick compares to concrete. I was just saying that well, actually kelpstone, not sea brick, but the kelpstone material is a lot lower density than concrete, so that makes it like beneficial in that way. It's also quite a good insulator. So and concrete it's much better than concrete in that way, which has its own uses. And also another revenue stream, I think, for the kelp farms is also selling the other components of the seaweed, such as sodium alginate and other components that come off that aren't used to make the sea brick. They can be sold and they're very valuable.
And by the way, Colton, I'll just introduce you because Colton is one of our lead researchers. Colton is materials engineer. He's been one of the lead researchers on the whole kelpstone product, and is pretty familiar with all the chemistry and factors like insulating properties, etc. I think one point you touched upon, Colton, that I'm very excited about is just that this is going to be an extra revenue source for seaweed producers. They already have the machinery and economic apparatus to get value out of the alginates and the extractions. This is going to be another market for the kelp residue, the fiber residue that's left over after that extraction process happens. So my hope for kelp producers is that it's just going to add income to their business model. And before I go to you, Brian, I'm just going to check. Janice, do we have any more questions?
No more questions, and we're heading up to 3:30. So, Brian?
Yeah, just wanted to wrap up that in our research with the Norwegians and the Australian cooperative research centers, we were finding that you can choose with large offshore structures to either make them flexible or strong as steel. Both are feasible to a point. I would encourage the flexible approach where possible, and to the extent the sea bricks become mechanically flexible, in addition to being design flexible, I think that presents a scalable opportunity. So the more flexible in a sense and resilient to the give and take of the sea, the better. Anyway, it's great to connect with all of you, and thank you, John.
Thank you, Brian. And on that note, we're at the hour, the hour and a half. I thank you all for staying around for so long. On the point of rigid versus flexible, I'm going to share the deck. In fact, I might just type it in right now. And at the deck.
John, can I just also let everyone know that Brian posted a link to the article that he referenced earlier. So if you're interested, there it is in the chat.
Thank you, Janice.
I've just posted a link to the deck that I walked through today. I think that came in, did it? Oh, no, it didn't. There. Oh, sorry, I didn't send it to everyone. There we go. So this is the deck that I shared. And at the end of it, you'll see that there's some links. One is the link to the technical white paper. So I invite you all, Michael and Brian and others in the room that are interested in, kelp farm design, please take a look through. I think you'll see that we have taken the flexible approach, and you'll see that as, even though we're talking about fairly rigid beams, the overall structure is going to be fairly absorbent of force. And that has always been a kind of a design driver. Also, on the business model and the carbon sequestration model, you'll also see at the end of the deck the link to the sheets. So there's a broad range of what we're gonna. I don't know where the numbers are going to land. I know that they're high. 1 million square kilometers may be too much, and maybe 100,000 kilometers. I invite your feedback to that, and and please join us in the Discord. And I'm sure there's going to be a great conversation happening there about how to improve it and flaws that have been uncovered, etc. So, in conclusion, Janice, yeah.
Not much from me. Thank you, everyone, for joining us. It's been awesome, John. Thank you for your presentation.
Thank you, everyone, for joining. Yeah, it's a pleasure.
Thanks, John.